Hello, welcome to my channel. In this video, I'm gonna talk about LC source free response. So let's get started. So let me first draw the circuit. So this is the LC circuit when it's source free. So we have an absence of input in the circuit configuration. So what will the response look like in a source free LC circuit, where this is C, this is L. This circuit has no input, but it has initial current and voltages. So say initial current IO, and this has initial voltage VO, the voltage across the capacitor, and current in the inductor. So we know that, um, or some of you might not know, that LC circuit has two dynamic elements. So L and C, these are two frequency dependent and dynamic elements. So because of this, the, this LTI system will generate a linear differential equation with constant coefficient of second order. So let let's get started. So in time domain, so before going to the equation, let me tell you something, that the source free response of the RLC circuit involves both current and voltage, and the response is an oscillating one. And we have assumed that the inductor and the capacitor is pure. There's no resistance in the two components, so the oscillating response will be a combination of sine and cosine, and the oscillation would go on continuously and for an indefinite time, as there's no resistance, there's no energy dissipation. So there's no resistance, so here R is practically zero here in this circuit. And the response will be both current and voltage. So the response will be both current and voltage, and it will be an oscillating one, which will be undamped, and which will oscillate for indefinite time. So here the initial current states that energy is stored in magnetic field inside the inductor, and the initial voltage states that initial energy is stored in electrical field across the capacitor. The energy stored in the electric field in the capacitor will uh, transfer to the inductor, and energy stored in the magnetic field of the inductor will go transfer to the capacitor, and this will happen continuously and for indefinite time. uh, and during this transfer of energy, it will create an oscillating voltage and current, and we are gonna see this mathematically, and in the later videos we are gonna see the transfer in visual terms. So here let me so in this operation there's no resistance, no resistor, so no energy dissipation. So in the previous videos of circuit analysis, we analyze the RL circuit, RC circuit. So there was at least one resistor with the capacitor and the inductor, but here we have both the two uh, dynamic elements, inductor and capacitor, but there's no resistor involved here. We have assumed it. So energy dissipation, no energy dissipation. So and oscillation, undamped. So resistance means damping, and absence of resistance will mean the system is undamped. So there will be no energy dissipation, only undamped oscillation. Energy will be transferred back and forth from L to C and vice versa indefinitely. This source-free LC circuit response, we have assumed zero resistance, and this is a second order LTI system. Mm, that's why the response will be both current and the voltage. There will be no energy dissipation, only undamped oscillation. Energy will be transferred back and forth from L to C and vice versa indefinitely. This is the basic um, result we have predetermined. Now let us derive the equation and uh, test our um, statements. So as this is an LTI system, we can it abides by superposition principle, and we can apply KVL KCL because of its linearity. So we are analyzing this in time domain first, then we will try the try to analyze this circuit in frequency domain. So in time domain, by both KVL and KCL. So by KVL, um, LDIT minus VT. See, this is inductor and this is capacitor, equals 0, no input. And by KCL, C capacitor d by dt, VC in time domain plus ILT equals 0. So we have got our two equation for the analysis. Now what to do? So let us replace the differentiation term by linear differential operator. So d by dt, let us replace it by d. So say vct equals ld il by t. Now let me substitute this in 2. So c d cd and cross ld ilt plus ilt equals 0, which gives us clc d square plus 1 ilt equals 0. Now this has become a second order differential equation with constant coefficients. So where the constants are L and C, and this is a second order. So second order linear ordinary differential equation with constant coefficients, because the power of d or differential operator is 2 here. So this is a different second order ordinary differential equation with constant coefficient. Now if we take the characteristic equation and solve it, we will find the response of this source free circuit, and we will only get the transient part of the circuit. We won't get any particular integral or steady state response because there's no source involved in it, and thus there will be no steady state response. So the characteristic equation the characteristic equation will give us the uh, the eigenvalues. So L C D square plus 1 equals 0, D square equals minus 1 by LC. So D equals plus minus J 1 by root over LC. Say 1 by root over LC is natural undamped frequency omega n. Say omega n, which is natural undamped frequency, is 1 by root over LC. So this will become plus minus j omega n. So we have assumed some things, and we have found this eigenvalue or this root of characteristic equation. Now let us find the final response of the LC circuit. So transient response, we know that transient response or complementary solution, what is in electrical terms the transient response. So in mathematical terms, in the complementary solution is ci e to the power lambda I t, I equals 1 to n. So this is the complementary solution, the uh, uh, all with all the eigenvalues uh, considered with their arbitrary constants. So this is the solution. So the transition response for LC circuit will be, so current IL t equals C1 e to the power j omega n t plus C2 e to the power minus j omega n t. So this, so if we break this complex exponential term, it will give us by Euler's identity equation, it will give us C1 cos omega nt plus j sin omega nt plus C2 cos omega nt minus j sin omega nt. Now ILT equals, say, C1 plus C2. We're just rearranging this, okay? Cos omega nt plus j C1 minus C2 plus sin omega nt. Now let us replace C1 plus C2 by C3. So C3 cos omega nt plus j C1 minus C2. Let us replace this term by C4. So C4 sin omega nt. We have to find the arbitrary constant. So let's go get into that. So here we have assumed the initial voltage and current across the capacitor and inductor respectively. So I L at t equals 0 is initial current equals C3 cos omega n dot 0 plus C4 sin omega n dot 0. So this term will vanish, leaving behind IO equals C3 dot 1. That's why C3 is initial current. Now we also know, VCT equals LDILT. So what will this give? This will give L, so IT is this, so C3 omega n sin omega n t. There will be a minus, so minus C3L plus c4 omega n cos omega nt. Okay, let me write this neatly. So there's obviously plus c4 omega n cos omega nt. We only did the differentiation of the value for il. We found solving the differential equation, the characteristic equation. Okay, so uh, after differentiating, mm, d here represents linear differential operator. We just um, um, d means differentiation in simple terms, so we just differentiated it and we got our value. So differentiation of cos is minus sign and differentiation of sine is cos. With the extra value omega n will go to the coefficient side. mm, and this is the answer. Now, so vc, voltage across the capacitor at t equals 0, is vo, the dc value, equals to L minus C C3 omega n dot 0 plus C4 omega n dot 1. Now this will give us LC4 omega n equals to VO. Thus C4 equals to VO by omega nl. So we have got all our arbitrary constants. C3 is initial current and C4 is initial voltage divided by omega L, omega n L. Can also be represented by VO by XL. XL is the reactance. Now that we have found our arbitrary constants, the circuit response in current is C3 is IO cos omega nt plus, this is plus, there's no minus term, so plus c4 is v, initial voltage across the capacitor, omega n, undamped natural frequency, l sine omega nt. So this is the response of the LC circuit, the current part. Now the voltage, we can get the voltage very easily. We will use VCT equals minus 1 by C I, say this is 1 by D, 1 by D IL dt. If you remember the number 2 equation, we are using that. Okay, so if linear differential operator D means differentiation, the 1 by D will mean integration in literally. So here minus 1 by C, so IL is this full term and we're integrating this. So yeah, let me write this down. So IO integration cos omega n t dt plus VO by omega n L cross integration sine omega n t. Now minus 1 by c minus 1 by c I o initial current in the inductor by omega n, and integration of cos is sine, obviously sine omega n t, and here it will be minus, because integration of sine will give minus cos omega t, so minus cos vo initial voltage across the capacitor divided by omega n. Here 1 by omega n will come from this integration, so omega n square l cos omega n t. So what will happen is minus I o omega n c sine omega n t, minus and minus will be plus, and omega n square is 1 by omega n c, we know that, so vo by 1 by lc cross lc, this will cut out, and cos omega nt. The voltage response of the LC circuit has the value VO, initial voltage across capacitor, cos omega nt, minus initial current omega n, the natural undamped frequency, C capacitance, sine omega nt. The response is both current and voltage. Okay, so now the complete in time domain analysis for the LC circuit, the source free response, the complete response, the complete response, the complete response is current equals initial current across the inductor cos omega nt plus initial voltage by omega n l sine omega nt, and the voltage, the response will be initial voltage cos omega nt minus io by omega nc sine omega nt. So this is the complete response where omega n equals 1 by root over LC. So this is the answer, this is the full answer in time domain analysis for the LC response. Now we will do the analysis of the circuit in frequency domain. So LC circuit is obviously an LTI system, so it's assumed linear, and because of that property we can apply Laplace transform. So let us apply Laplace transform, Laplace and inverse Laplace this. So this is a capacitor with initial voltage and inductor with initial current. We use the voltage source analogy. So initial current is LIO. After Laplace transformation, the inductor is SL and capacitor is 1 by SC, and initial voltage is VO by S, obviously DC value. And this is for KVL, and we will use also another analogy, which is, sorry, this there won't be any Laplace, only one Laplace transform. So we will also use the current source analogy. So for the current source analogy, 1 by SC is L, and initial current is IO by S, DC current, and initial voltage is, in current source analogy, CVO. So we will use this circuit for KVL and this circuit for KCL. So by KVL and KCL, so applying KVL in this circuit, we find S L I S plus 1 by SC I S equals VO by S plus LIO. Now say 1 by SC square LC plus 1 IS. You can understand what I have done here. I have just taken out the common and rearranged this, and this is VO by S plus LIO. Now S square LC plus 1 IS, this is the response. So CVO, we have taken this in the right side, to the right side, plus SLCIO. Let me write it here. IS equals CVO by S square plus, sorry, S square LC plus 1 plus SLCIO by S square LC plus 1. Now IS equals, so CVO by S square plus 1 by LC, taking out the LC term, plus SLC, initial current, S square plus 1 by LC, taking the LC common, so LC cuts out, C cut out, so this will give by S square plus omega n square we assume that 1 by L root LC. So let us assume where here omega n equals 1 by root over LC. So this will become s square plus omega n square plus SIO by s square plus omega n square. Now what we're gonna do now, mm, so you can understand what I've done here and take a look if it makes sense to you. And here I have I have nothing to do, just write it as it is. Now we are gonna do inverse Laplace here. Is equals VO by omega n L. This is obviously sine omega n t plus IO. This is cos omega n t. So thus far we have done we have solved the current response of the LC circuit in frequency domain using KVL. Now let us apply KCL in this circuit to find the voltage response of the LC source free circuit. So by KCL in this circuit, say at node A. So we have assumed the initial current through the inductor and capacitor. So let me write the KCL equation, current equation. So V S by SL plus SC VS equals CVO minus IO by S. Now let me take the common 1 by SL S square LC plus 1 VS CVO minus IO initial current S by S square LC plus 1 VS equals SLCVO minus LIO. Hope you understand this term, this part. Now VS equals to SLCVO by S square LC plus 1 minus LIO by S square LC plus 1. Now SLCVO by S square plus 1 by LC common minus LIO by S square plus 1 by LC. So cut this whole thing out. So VO S by S square plus 1 by LC minus IO by C, and take an omega extra, omega n by S square plus 1 by LC. Now let us try the inverse Laplace. Vs. This will give Vo cos, sorry, cos omega nt minus Io by omega nc sin omega nt. After our derivation, we have found the voltage response of the LC source phase circuit, and this is the answer. Now let us summarize the complete response in frequency domain. So now in frequency domain, after our derivation applying KVL KCL in these circuits, we have found our response for the LC source phase circuit. The source free response is in frequency domain after applying inverse Laplace transform. T equals IO cos omega nt cos omega nt plus V or initial voltage across the capacitor by omega n L sin omega n t, and voltage equals VO cos omega n t minus IO by omega n c sin omega n t. Thus, this is the answer where omega n is 1 by root over LC, and omega n is the undamped, so undamped natural frequency. Undamped natural frequency omega n is 1 by root over LC for the LC circuit. So this is the source free response of the LC circuit in both time and frequency domain. We are gonna transform the equations in amplitude phase form, so it will be very useful for our later discussion and in your encounter with um, second order systems in control systems or in system analysis or circuit analysis, where you have to analyze the circuit in time and frequency domain both. So let's see what the equation of the response looks like in amplitude phase form. So the current response of the circuit was IT equals initial current cos omega n t plus initial voltage across the capacitor by omega n L sin omega n t, where omega n equals 1 by root over LC. This is natural undamped frequency. So let us assume some things here. Say initial current, because of the oscillation, it becomes I m cos delta I. Delta is the phase between current, the two currents, this and this, and VO by omega n L. This is also current, so this is equals to I m sine delta I, which gives us I m equals to root over IO square plus VO by omega n L square. And we can also find delta I, which is tan inverse VO by omega n L I O. So these are the considerations, the assumptions we have made to get the amplitude phase form. So here let me write response in amplitude phase form. Phase amplitude phase form. So here it will look like I am cos delta I cos omega nt plus sine delta I sine omega nt. Now we can easily write this. So by trigonometric formula, this cos omega n t minus delta I. So if you know the trigonometric transformation, the trigonometric formulas for cos A cos B sin A sin B, you will understand this derivation. So this is the amplitude phase form for the current of the response. We can also write this in phasor form, where I m minus delta I. So this is the amplitude phase form. Now for the voltage part, so now for the voltage response part, so V t equals initial voltage of the capacitor cos omega n t minus initial current by omega n c sine omega n t. Now let us assume like before. So say VO is Vm cos delta V, and the voltage minus IO by omega in C is Vm sine delta V. So Vm will be root over VO square plus IO by omega in C. You can put minus here squared, and delta V is tan inverse minus IO by omega in C V VO. We can also write this minus tan inverse because tan minus theta is minus tan theta. So IO by omega in CVO. This is the assumption we have made now. Let us write the form. So Vm, take the common Vm out. So cos delta V cos omega in T minus, sorry, this will be plus sine delta V sine omega in T. Now this is also from trigonometric formula. We can write this Vm cos omega in T minus delta V, and in phasor form this is Vm minus delta V. So this is the amplitude phase form for the voltage response of the LC source free circuit. So now in summary we can write the source free response of the LC circuit uh, for current IT equals IO cos omega in T plus VO by omega in L sine omega in T equals Im cos omega in T minus del I, and the voltage response is VO cos omega in T minus IO by omega in C sine omega in T equals Vm cos omega in T minus delta V. The response, uh, this is the general form, this is in amplitude phase form, and we from this we also see that the phase delta I plus delta V is pi by 2 equals to 90 degree, and that voltage Vt leads current It by 90 degrees. I think voltage leads, that should be the case. Yes, voltage leads the current It by 90 degree, and this is the final expression for the source free response of the LC circuit. So that's it. Thank you.